talk about the inexact differential. Again, I typically call it a del, D-E-L-L. The inexact differential is that it's where we're dealing with something that may be a function of more than one variable. So again, I don't know if anybody's ever explained that to you. I just want to make sure, because when you see that in the text, it might be confusing. What the heck is that symbol? It's just a D. It still represents a differentially, infinitesimally small amount of this quantity. This is a tiny little slice of W. This is a dW. This is a dQ. So this is a tiny little differential, infinitesimally small slice of Q. And that's all that differential represents. Doesn't matter what kind of differential it is, whether it's exact, partial, or inexact, they're all referring to a differentially small, infinitesimally small slice of this quantity. Okay? And the shape is just designating, do we know it's a function of one variable, a function of multiple variables, or we're just not sure, so we're going to have to leave it as inexact. Okay? Again, just didn't want you to see that and not have any context for that. Okay? So why does that matter? Well, here's the thing. So we're going to continue talking about properties. We mentioned properties in the previous lecture. We said properties, things like pressure, temperature, volume, these are dependent only on one variable. And these are only dependent on one variable, that is the state of the system. And so if we're talking about temperature, we're going to use a regular exact differential for temperature, pressure, or specific volume or total volume. We're going to use just a regular exact differential D for those. Okay. Now, on the other hand, because these are what we call path independent, I just realized I've got another little bullet point there. Okay. So these are path independent. They don't. It does not matter, right? It does not matter how I get from state 1 to state 2, or from one state to another. It does not matter how I get there. All the temperature or the pressure, the volume really cares about is where it's at, not how it got there. Now, on the other hand, heat and work are what we call path dependent. Okay? So, for example, let's say that we have, well, let's just do this on paper. I think I make this a lot cleaner on paper. So heat and work are path dependent. It's important to know how did we get from one state to the other, right? So, for example, let's say that I've got a chair, right? I've got a chair, and we've got an instructor. This is how I draw people, right? So I've got an instructor ready to move this chair, okay? And so let's say we have a property equals the location. The location of the chair, we can call that a property. Right? So this is location 1, S1 we'll say. And let's say that the instructor somehow moves that chair to location 2. So we'll say location S. That's my property's location. Okay. Now, let's say that let's say the way the instructor gets the chair from here to there, from S1 to S2, is just this. This is work for path A. All right? So that's how the instructor is going to get it from position 1 to position 2. Again, the position doesn't really care how it gets there. It just needs to know where it's at. But the work required to get from here to there does need to know, how did you get there? Because let's say that instead the instructor pushes it all the way around the room and then maybe outside and sits down for a minute to take a breather and then comes back inside and pushes it to location 2. This is path B. So you can see that the work for path B is going to be much greater than the work for path A. Why is that? Because heat and work are dependent on the path. They're dependent on how did they get from one location to the other. Right? Convoluted path is going to require more work than a straight line path. But the position, the location, doesn't care. Does not care how it got from here to there. It only needs to know where it's at. Okay? Properties are the same way, any kind of property. Pressure, temperature, the pressure on the chair, the temperature of the chair, the volume of the chair. None of that matters how it gets from one state to the other. Those are path independent. So we use exact differentials because it doesn't matter. It's only a function of one other thing. But inexact may be a function of multiple things. And this path here, if I encounter some ice somewhere through here, if I'm just scooting that chair along and all of a sudden I encounter some ice, now I don't need much work because there's not much friction. Or if I'm dragging it across gravel, there's more than one, or possibly more than one variable at play. Okay? That's the reason for the inexact differentials when we're talking about differential small slices of heat and work. Okay? So I'm hoping that helps a little bit when you see these weird shapes. What the heck is that? I just had Calc 2 or just a little bit of calculus. That's okay. Okay? All right. So we talked a little bit about heat. We said heat occurs through what? 3 methods heat occurs through. If you don't know them, pause and let's go look those up. Pause. Okay, so what are the 3 methods of heat transfer? Right? And then types of work. So we talked a little bit about heat. Let's talk a little bit about work, types of work. Now, in your physics class, you've already talked about applying force through a distance. And again, I've mentioned, if they didn't already tell you, I hope they did, it's the integral of force with respect to distance. Now, another type of work, we're going to encounter a number of different types of work, potentially encounter a number of different types of work in this course. A common one, kind of the foundation of thermodynamics, is the work done by an expanding gas. And we're going to focus in Chapter 4 and then beyond a lot on that. We'll mention it here briefly in Chapter 2. You will encounter from time to time electrical work. Okay? So we need to talk about how do we quantify that. And then there's a couple of other ones here that we might encounter from time to time. So let's put some tools in place for those. Okay? So again, work done for an expanding cylinder, a gas expanding cylinder. So again, work is going to be the integral of force with respect to distance. So here I'm going to say that work is equal to the integral. What causes the force in an expanding, if I've got a gas trapped in a cylinder and I heat that gas up and that gas wants to expand, what it's going to do is it's going to cause that cylinder to expand because the pressure inside that cylinder increases or decreases as I change the temperature, as I add or remove heat from that cylinder. And the distance that pressure travels is through the volume of the system. Work is equal to the integral of pressure with respect to volume. And what we do is we say, well, this is what we call the boundary work, and we'll compute it in the out direction, so we'll assume this is a work out term. The subscript B stands for boundary work. This is the work done by the boundary as it expands or contracts. And we're going to integrate this from an initial volume to a final volume. And if I integrate from initial volume to final volume, pressure with respect to volume, this is going to give me the work out. If I have a negative sign, that just tells me it's work in, and that's not too big a deal. Again, a lot of focus on this later in the course. I'm just kind of introducing it at this point. Okay? All right, what else we got? Electrical work. So, electrical work, which let's start first with a quantity we call electrical power. W dot sub E. Again, if I put a dot above a variable, what does that mean? That's really important. Dot above a variable per unit time, right? So if I have a dot above work, that means work per unit time. We call that power. Power is equal to the integral, no, not the integral yet. That comes later. power is equal to the product of a quantity we call voltage. I'm going to write that out. A quantity we call voltage and a quantity we call current. Now, I'm not expecting you to be experts in electrical science. I'm not expecting you to have had electrical science or even physics too at this point. Electrical and optical physics. I'm not expecting that. We can just talk about this here. Now, normally, what we do is we say that this is electrical work is equal to, we normally use a V and an I for voltage and current, respectively. Now, we very rarely deal with it, but remember, we've got our cheat sheet back here. And remember, I've got V's already. I've got several different V's already. Okay, so this is yet a fourth V that we'll deal with. So most of the time, if I'm dealing with voltage, I deal with it so rarely in this course that I normally just write out the word voltage. Okay, but if I'm dealing with electrical, if you see this symbol and you see a V here, they're referring to voltage, not speed. Okay, so just be aware of that. If you want the electrical work without the dot, again, this is a rate. So to get the total from the rate, I need to integrate that rate with respect to time. Now notice what happens if voltage and current are constant. We call that DC conditions. So if I'm dealing with constant voltage and constant current, then the power is constant. It's not a function of time, and so I'm just multiplying the power, the electrical power, by the time, and that gives me the electrical work. Okay. Units here, 1 volt times 1 amp. An ampere or an amp is the unit of current. Volt is the unit of voltage. That is equal to 1 watt, which is a joule per second. Okay, so just be aware of that. You won't encounter electrical power or electrical work very often in this course, but when you do, it's pretty simple to deal with. Okay, the hope is you say, hey, wait, I saw work in chapter 2. I need to go back to chapter 2 or my notes from chapter 2 and figure out how do I do that. And that's okay. Okay, next type of work here, and I could probably do this off the top of my head, but I'm going to grab my notes just in case I need them here. Alright, so, and again, as I mentioned before, normally would have these PowerPoints on a smartboard, and I could just draw on the smartboard as we go along. This kind of works okay, I'm hoping. And I'm hoping this is helpful for you. So shaft work, right? So here's the thing. You've got, again, work. Now, we've got work being the integral of force with respect to distance, right? Well, if force is equal to a quantity we call torque divided by radius, right? So T, this capital T, this funny looking capital T, is what we call torque. If you've had statics, that's very similar to a moment. That is a force applied at a distance, and the distance, R, is the radius of the rotating shaft. So what we're quantifying here is we're talking about the work done by a rotating shaft. Let's say I've got a motor or an engine with some kind of rotating shaft output, and I want to find what is the work done by that rotating shaft. Well, again, torque is essentially the product of a force and a distance, and a torque is a force that, or a torque is a quantity that will cause rotation. Okay, so the tendency to cause rotation, the torque, is going to be the force times the radius about the point of rotation. Okay, so to plug into this integral here, T over R is equal to F, and the distance, S, right, if the force is constant and rate of rotation is constant, then that S is just simply the circumference of the outer edge of the shaft, 2 pi r, giving me the circumference of the shaft, multiplied by n, n being the number